Welcome to O Mass Spectrum, Speak to Me. The mass spectrum contains a lot of information, but it's up to the chemist to interpret the spectrum and draw the information out. If a peak is seen for our molecular ion peak, it tells us the mass of the molecular ion and thus the mass of the molecule. But unfortunately, this peak is often absent. Fragment peaks can give us clues as to the composition and structure of our molecule. So let's examine the nitrogen rule. If a compound has an odd number of nitrogen atoms, then the molecular ion peak will have an odd mass. It may have any number of carbon, hydrogen, halogen, oxygen, sulfur, silicon, or phosphorus atoms in it. If a compound has an even number of nitrogen atoms, then our molecular ion peak will have an even mass. For example, if our molecular ion has a mass-to-charge ratio of 128, then it can have either 0 or 2 nitrogen atoms, but not 1 nitrogen atom. And generally, if the mass-to-charge ratio is only 128, then we probably can't have more than 2 nitrogen atoms. For aromatic compounds, electron ionization usually gives a significant molecular ion peak. For example, the molecular ion peak is the dominant peak in both the benzene and biphenyl mass spectra. The next higher peak, M+1, so that's this one here for benzene and this one here for the biphenyl, gives us some information on the elemental composition. So carbon is 98.93% carbon-12 and 1.07% carbon-13. Hydrogen is almost all hydrogen-1 and only 0.012% deuterium. Thus, the intensity of our M+1 peak for CnHm should be this, where we have the intensity equals N times 1.07%. So this is the contribution from the carbon-13 plus M times 0.012%. This is the contribution from the deuterium, the H2. For benzene, the molecular ion peak is at a mass-to-charge ratio of 78. And the expected intensity of our mass-to-charge peak at 79 is 6 times 1.07% plus 6 times 0.012%, which is 6.55%. And the observed intensity is 6.5%. And note that an intensity within about 10% of our expected value is within the precision of most mass spectrometers. Ions that contain chlorine or bromine have distinctive isotopic peaks that you can see here. We've got, if we have a single chlorine atom, then we've got that ratio. If we have 2 chlorine atoms, then we're going to have this ratio between 3 peaks. If we have 3 chlorine atoms, then we'll have a ratio between 4 peaks. 1 bromine will give us an almost equal split between 2 peaks, 1 at x and 1 at x plus 2. If we have 2 bromine atoms, then we'll get this split between 3 peaks. 3 bromine atoms gives us 4 peaks. 2 bromines and a chlorine will give us this one. 2 chlorines and a bromine will give us that one. So the integer value of Mz is not enough to identify the elemental composition. For example, an ion at a mass-to-charge ratio of 87 may be either C5H8O+, which is at 84.0593 Daltons, or it may be C6H12, which is at 84.09335 Daltons. This 87 is supposed to be an 84. If our spectrometer has sufficient resolution, then we can differentiate these 2 peaks. And these types of instruments can resolve 0.001 or less at a mass-to-charge ratio of 100. We've got the double focusing mass spectrometer, a time-of-flight mass spectrometer, an Orbitrap, or a Fourier transform ion cyclotron resonance mass spectrometer. So suppose we know the composition of a molecule or ion, and we want to know the structure. The number of rings and double bonds, R plus dV, is given by this equation, where C here is the number of group 14 atoms, so carbon, silicon, and so on. H is the number of hydrogen or halogen atoms, and each of these forms a single bond. N there is the number of group 15 atoms, so nitrogen, phosphorus, and so on, and each of these will form 3 bonds, and then plus 1. So let's look at an example. Here we have a molecule containing some ring and a double bond, and we've got a large variety of other atoms bonded to it. We get an R plus dB of 14 plus 1 for the 14 carbons plus 1 silicon, minus 22 plus 1 plus 1 for the 22 hydrogen atoms, plus the 1 chlorine plus the 1 bromine, that's divided by 2, plus 1 over 2, where each one of those is the nitrogen and the arsenic here. Then we have plus 1, and that gives us 5, and we can see that the molecule has 1 ring and 4 double bonds. We've got the 1 ring here, 3 double bonds in that aromatic ring, and 1 double bond over here in our carbonyl. And suppose we obtain these 2 spectra from 2 unknowns. Now, I know I've got the structure of our molecules here and here. This one is from 2-hexanone, and this one is 4-methyl-2-pentanone. So in both cases, the molecular ion peak M+ is at an MZ of 100 over here and there. But how do we know that these are the molecular ion peaks if we have unknowns, if we don't know what the structure of our 2 molecules are? Well, the molecular ion peak will be at the highest significant mass-to-charge ratio peak that's not attributable to isotopes or background. The background may arise from sources such as pump oil in the spectrometer or stationary phase from a gas chromatography column. The intensities of isotopic peaks at M+1, M+2, and so on must be consistent with the proposed formula that we have. So, the peak at the highest mass fragment must also correspond to a reasonable mass loss from our molecular ion peak. For example, the mass loss of 3 to 14 or from 21 to 25 Daltons is pretty rare. Common losses include 15 from the methyl group, 17 from OH or ammonia, 18 from water, 29 from C2H5, 31 from OCH3, 43 from CH3O or C3H7. If a fragment contains A atoms of element X, then there must be at least A atoms of X in the molecular ion. In both spectra, the highest mass-to-charge significant peak is at mass 100. And in both spectra, the highest mass fragment is at mass-to-charge ratio of 85, representing a loss of 15 Daltons, which is probably the methyl peak here. Since a mass-to-charge ratio of 100 is even, then there are an even number of nitrogen atoms, and remember here that 0 is even. So in both spectra, N+1 has an intensity relative to our molecular ion peak of 6%, and thus we can estimate the number of carbon atoms as 6. With 6 carbon atoms and no nitrogen atoms, because the mass is too low for 2, then one possible formula is C6H12O. And C6H12O requires 1 ring or double bond, and you can see here that in 2-hexanone we have 1 double bond. In the 4-methyl-2-pentanone we also have a double bond. So let's examine how the 2-hexanone can fragment. Our molecular ion is likely to be derived from 2-hexanone by removing a non-bonding electron from the oxygen, because this is going to be the lowest ionization energy. So you can see in each of these cases we've got an electron missing from our oxygen here. Now in reaction A, then the carbon-carbon bond adjacent to the carbonyl splits such that 1 electron goes to each of our carbon atoms. So we've got this bond being split, and 1 electron is going that way and 1 electron is going this way to the oxygen. The products then are the neutral butyl radical here and our ion over here. The neutral species are not going to be detected in mass spectrometry, so only our ion will be observed at mass-to-charge ratio of 43. In reaction B, the other carbon-carbon bond adjacent to the carbonyl will split, with 1 electron again going to each carbon atom. So again, we've got our homolytic cleavage of this bond, and now we've got this ion and the CH3 radical. So we've got our methyl radical and an ion with a mass-to-charge ratio of 85. Remember, this is the major fragment that we see in the mass spectrum. In reaction C, then that carbon-carbon bond undergoes heterolytic cleavage, which means that both electrons go to 1 atom, and the products are the methyl ion and a neutral radical. So we've got this bond being broken, both of those electrons are going this way, and that means that now we have this radical and a CH3 plus ion. So we can have the bond between the 4th and 5th carbon atoms break to give us the CH3, CH2 plus, which is a mass-to-charge ratio of 29, and than this other ion here. And remember that the nitrogen rule says that a molecule containing only carbon, hydrogen, halogens, oxygen, sulfur, silicon, phosphorus, and an even number of nitrogen atoms, as in 0, must have an even mass. So a fragment with an odd mass is thus missing a hydrogen atom. Note, however, that the peak at mass-to-charge ratio of 58 is an even mass. This is corresponding to a loss of a fragment with mass-to-charge ratio of 42. So reaction D shows the McLafferty rearrangement leading to the loss of a propene molecule which has a mass of 42. So we've got the McLafferty rearrangement here. You can see that this hydrogen is going over here to that oxygen, and we lose the propene, and now we've got that hydrogen up here on the oxygen. So the major difference between the spectra for 2-hexanone and 4-methyl-2-pentanone is the presence of a peak at mass-to-charge ratio of 71 for our 2-hexanone. So that's this peak here. This peak is corresponding to the loss of the ethyl radical CH2CH3 from 2-hexanone. And there's no simple way for the 4-methyl-2-pentanone to lose that ethyl radical. So, interpreting the mass spectrum of an unknown compound may thus give us clues as to the molecular structure, but it takes a good deal of effort and experience to interpret these spectra correctly. So that was, O mass spectrum, speak to me.